Hello AP Stat students, this is Mr. Hazelhorst here with your Chapter 6 Section 2 video. I just want to make note we won't have a video over Section 1. That's not a section that we will cover. It deals with simulation, which is just kind of an extra concept in our book and something that we don't really use a whole lot, so we're not going to spend too much time on that at all. We'll mention it briefly in class once we get back together after the weekend. But let's get into your Chapter 6, Section 2 video. What we're going to focus on today are probability models. And hopefully some of the things that you see today are going to be review from what you learned in maybe an Algebra 2 or pre-calculus class as you dealt with probability. Or for those of you who took Prob and Stats, you're going to see some similarities there as well. But there's also going to be probably some new terms and symbols that come your way. So we'll want to be prepared for those. So let's get into it here. So the first thing we want to talk about is the idea of probability, which is just simply that chance behavior is unpredictable in the short run, but if we study it long enough, there begins to become this predictable pattern that we want to establish. And that's what we're going to look at here in Chapter 6, is can we establish this predictable pattern in the long run? It doesn't help us on any individual trial, but it does help us to see tendencies and over large periods of time, again, be able to make some wise decisions if we think back to the video that we watched about probability. All right, and so this idea of random is going to be extremely important. So random is just simply a description of a kind of order that only emerges in the long run. All right, when we say that is random, that's because we know in an individual trial anything can happen, right? But over a long period of time, that randomness all of a sudden isn't so random. And that's what we're studying here when we talk about probability. A term just to be aware of is the idea of empirical. And empirical means that it's based on observation. That might be a term you've heard in a science class. If you do an empirical study, you just simply sit back and observe. And this idea of empirical is really the history of probability. If you think back to the video that we watched in class, a lot of those early examples were just mathematicians going out and seeing what happened in the world and then trying to explain it. And that's where probability really emerged. Your book gives some great examples of empirical probability. Now, some of you might consider what I'm going to share with you a waste of time, which I would kind of laugh at considering the amount of time you spend on Twitter and silly videos on YouTube, but that's beside the point in a conversation for another day. But here's a couple of examples from your book. All right, a French naturalist, Count Buffon, he tossed a coin 4,040 times and came up with 2,048 heads, or just under 51% heads. Okay. In 1900, an English statistician by the name of Carl Pearson, he tossed a coin 24,000 times, which resulted in 12,012 heads, or a proportion of 0.5005. All right? And then one more, while John Kerich was imprisoned during World War II by the Germans, he tossed a coin 10,000 times, and his result was 5,067 heads, or a proportion of 0.5067. Now I'm going to guess that hearing those numbers, you're really not surprised to hear the outcomes of those values. You know the probability of flipping a head on a coin is 0.5, and all of those values came out to be close to that value. All right, and again, that's the idea that in a long run, we can come up with a predictable pattern, and that predictable pattern is that 50% of the time, we are going to come up with heads. All right. Now, that doesn't help us determine what the coin is on any individual trial, but again, it does give us an idea in the long run. So as we talk about probability, that's what we're going to be focused on, okay? So let's get into some terminology here, right? Some terms that are going to be important for us to be able to understand as we work through probability. So first off is a sample space, and you'll oftentimes see this represented with a capital letter S in our textbooks. All right, but this is just simply listing out every possible outcome in a situation. We'll do an example of this in just a moment, okay? Second term is an event, which is any outcome or set of outcomes for some random phenomenon that we're going to study, okay? So when we talk about flipping a coin, All right, that set of outcomes, those events, would be heads or tails. And finally is the idea of a probability model, which is just simply a mathematical description of a random phenomenon. And it's going to be made up of two parts: the sample space, every possible outcome, and then assigning a probability to each of those outcomes. All right? And again, we'll look at an example of this in just a moment as well. All right? So let's work in an example problem and begin to look at this idea of sample space, and we'll work our way from there. All right? So we want to describe the sample space of flipping a coin and rolling a die. All right? If we performed those two tasks at the same time, or one following the other, wouldn't really matter. We want to list out everything that could possibly occur in that setting. Now, one way that we do this in mathematics is to use a tree diagram. A tree diagram is just an easy way that we can organize the sample space of a series of tasks. Okay? So as you look at the definition here, it's just a diagram used to represent a sample space where each level represents a task. All right? So in this case, we're going to have two levels to our tree diagram because we need one for flipping a coin and one for rolling a die. We have two tasks. And each branch of the tree would represent a possible outcome. All right? So let's diagram this out real quick. So I'm going to start out. It doesn't really matter which one you start with. I'm going to go ahead and start with the coin since that's listed first. So from a point, we're going to have two branches. And we know the outcome of flipping a coin is heads or tails. So I draw those out. All right, so there's one level of this series of events. Okay? The next level would need to represent the rolling of the die. And so we know if we roll a die, this will just be a standard six-sided die. There are 6 different outcomes. And I need to draw those off of each of the previous outcomes. Okay? And so what we have here is just a diagram representing the entire sample space of flipping a coin and rolling a die. And if I work from the top of the tree to the bottom, I have, again, what we would describe as a possible outcome. All right, so if I start at the top and work my way down, all right, I could flip ahead and roll a 4, right? That's one of the branches on this tree diagram, all right? Head and a 4. And we could go through and do that with all the outcomes. And we can see when we get to the bottom of this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes that are present in this series of tasks. Okay? Now, the idea of the sample space, right, oftentimes we'll use set notation to represent the sample space. So if I was going to list out every possible outcome in this setting, and I was going to use set notation to do that, right, we'd go S is equal to, and then we just list out every possible outcome. And again, we have them all organized here, so we'd have a head and a 1, a head and a 2, head and a 3, head and a 4, head and a 5, head and a 6, and we have a tail and a 1, tail and a 2, tail and a 3, tail and a 4, tail and a 5, and tail and a 6. Seems a little monotonous, but that would list out the sample space in set notation, which again is something that we will oftentimes do. And you'll see this at times on your homework, and you'll see this at times on a test or a quiz as well. So set notation is something that we want to be aware of. Okay? All right. Well, let's tackle another problem. All right? Here it says, how many 3-digit numbers can you make? Okay? Now, the first thing that we need to address is how many digits are there? Oftentimes people will say 9, but they're forgetting the digit 0. All right? 0 is a number as well. All right? If you like to ignore 0, I consider you a numberist, which is kind of similar to a racist, but dealing with numbers. All right? 0 is a number 2. Treat it as 1. All right? I'll get off my soapbox. So let's talk about another simple method that we can use to answer questions such as these, and it's what's known as the multiplication principle. And the name tells you basically exactly what you're going to do. You're going to multiply. Right? So here's the definition of the multiplication principle. It says if you can do one task in n sub 1 number of ways, and you can do a second task in n sub 2 number of ways, then both tasks can be done by just simply multiplying the ways that each one can be done individually. All right? Now, let's go back to our tree diagram problem and apply the multiplication principle there. So if I go back to my tree diagram, how many outcomes are there for flipping a coin? Well, we know there's 2. How many outcomes are there for rolling a die? Well, we know there's 6. And if we take 2 times 6, we get, that's right, 12. All right, and 12 was how many outcomes we ended up in total with our tree diagram. All right, so a tree diagram is helpful if we want to know what the possible outcomes are. And then the multiplication principle is extremely helpful if we just want to know how many outcomes there are. All right, we don't really care exactly what they are. We just want to know how many there are. All right, so let's apply this problem. Let's say we want to figure out how many 3-digit numbers you can make if each digit can be used only once. All right, so what I like to do a lot of times is I like to draw out my tasks. So I have 3 separate tasks in this problem. Right? I have my first digit, my second digit, and my third digit. So I'm just simply going to list out all of those. All right? So if each digit can be used only once, all right? And that'll be important here. All right? So my first selection, I have 10 different digits, 0 through 9, that I can select. But when I get to my second selection process here, because each digit can be used only one time, all right, we're going to now reduce this down to 9, because whatever digit I used in the first slot, I now can't use again. And then I get to my third slot. Again, I can use only each digit only one time, so I've already used 2, so now I only have 8 options left. All right, so we just simply multiply these together, 10 times 9 times 8, and we end up with 720 different 3-digit numbers where we use each digit only one time. All right, that's a simple application of the multiplication principle, but this is something that we'll use quite often here in Chapter 6. All right, so let's get into a little bit of notation then. All right, so going to be just some notation, some terms, and so on coming your way. A lot of information here over the next couple of slides, but if you printed off the notes, you can just kind of sit back and enjoy the show here. All right. So the first piece of notation that we want to be aware of is what's known as a union symbol, which looks like the letter U. And we will see this sort of notation quite often. All right, we'll see A union B. And what that means is A or B. All right, we associate the word union, we associate the concept of union with the word or. All right. Now, we also need to be aware of the phrase empty event. All right, which is kind of looks like our no solution symbol. All right, if we see an empty event symbol, that no solution symbol, that means that an event has no outcomes. All right, and a lot of times we'll see this as we start to pair events together, not necessarily in a single event, but there's a lot of times that we just can't do certain things together. That's impossible. There's no way, so there's no outcomes. All right. Third term is the idea of the intersect, which is an upside down U. All right, and A intersect B we associate with A and B. Now, it would be wise at this moment to kind of stop and make sure we know the difference between or and. And there was a pretty funny series of commercials about a year ago. I don't really remember what they were selling, but so it's a bad commercial since I don't remember that. But I remember the concept of it, and they were talking about how there's a difference between and or, okay? And so they said, here's some nuts and bolts, and my favorite one was they were putting a pool together, and so they used the nuts or the bolts. And as they're saying that, the pool falls apart and it all goes wrong, right? But we know and, if we use the word and, that means whatever characteristics we're describing, you have to have both of those. If we use the word or and a couple of characteristics, you only have to have one of those. You might have them both, but you only have to have one. All right, so there's a big difference between those words, or and. It's important that we can recognize that. Okay? So if A and B are disjoint, all right, that means that A intersect B, so A and B has no outcomes. Okay? So we'll go through some thinking about this here in just a moment, but let's talk about this word disjoint. Okay? Disjoint, and other times it's commonly referred to as mutually exclusive. For those of you who took the Providence Stats class here at South, that's probably the term that you used. And mutually exclusive just means we have two events that have no outcomes in common, so they never occur simultaneously. All right, and if we look here, this is just a simple Venn diagram. Notice that we've got the capital letter S in the box, so that's telling us that this box is representing the sample space of this setting. All right, and in this situation, you could be in event A, you could be in event B, but based on how this diagram is drawn, it's impossible to be in both at the same time. All right, an example of things that would be mutually exclusive, you cannot be a freshman and a senior at the same time. All right, those events are disjoint. You can be one, you can be the other, but you cannot be both. We think about a math class, right? You cannot pass a math class and fail the same math class at the same time, right? Those are mutually exclusive events. They don't have anything in common. They can't occur simultaneously, all right? So that's a big concept that we want to be aware of. All right, so let's get into some probability rules here. So 4 rules of probability. First off, is just simply the state that a probability has to be some number between 0 and 1. We cannot have negative probability values. We cannot have probability values that are greater than 1. Now, we need to clarify here. Sometimes we'll see probabilities given as a percentage, right? So we might say there's a 50% chance, all right? But remember, percentages correspond to decimal values. So 50% is the same thing as 0.5. All right. So when we say this rule, we're not dealing with percentages. We're dealing with them in their decimal value. Okay. Rule number 2: the sample space in a probability model always has to have the sum of 1. So if we're going to list out everything that can possibly happen in a given situation, and we also had the probabilities of each of those things, to be a true sample space, they have to add up to 1. That's a requirement. Okay. Rule number 3. If A and B are disjoint, then we can apply what's known as the addition rule for disjoint events, sometimes referred to as the addition rule for mutually exclusive events. Okay? So again, if they cannot occur simultaneously, and I want to find the probability of A or B, I just simply add their probabilities together. The key there being they cannot occur simultaneously. All right, we'll look at an example of this formula in just a moment. And then finally, we have the idea of the complement of an event in probability, okay? And that's if we're given the probability that something does occur, we can find the probability that it doesn't occur by just subtracting it from 1. All right? So pretty soon here, we're going to be rooting for some snow days, and we're going to see some probabilities popping up on the weather forecast if you start watching the news. You know, and if the newsman says, well, there's an 80% chance of snow tomorrow, well, we know then the probability that it doesn't snow is 20%. Right? That's the idea of the complement. Very simple. All right, so let's look at an example of a couple of these rules. All right, so here we have a sample space, right, of color of candy, right, dealing with the M&Ms here. Right, so we've got brown, red, yellow, green, orange, and blue. And we have the probabilities of each of those colors. Okay, so the first question that we have to ask is, what is the probability of drawing a blue candy? All right, so we look at this and we say, well, blue's not given to us, so I don't know. All right, well, if I go back to the rules that we just covered, we know that the sum of the probabilities in a sample space has to equal 1. So if I know all of the other probabilities, I know that the blue candy's probability has to be whatever will make this distribution total 1 when added together. All right, so if we do that here real quick, we've got 0.26 when we add the first two together, 0.4, 0.56, 0.76. So the probability of us obtaining a blue candy is 0.24. Okay, very simple. All right, so the probability of a blue candy, might as well use a blue marker. is 0.26. Because again, that's the probability that it takes to add up to 1. All right, so then it asks us, what's the probability of drawing a red, yellow, or an orange candy? Now, the word that we want to notice in this problem that should stand out to us is that we've used the word or. Right, so we're not saying it has to be all of those, because in fact it can't be all of those colors. Right, we know M&Ms come in one of those 3 colors, but it's impossible to have an M&M that is red and yellow and orange, or red and orange, or yellow and orange, and so on. Right, so these are disjoint events. They are mutually exclusive. They do not occur simultaneously. So based on one of the rules that we just covered, to find this probability, all we need to do is add together their individual probabilities. So the probability of being red is 0.13, probability of being yellow, 0.14, and the probability of being orange is 0.2. So we're just simply going to add these values together. And if we do that, we know there is a 47% chance that you are going to select a candy that is red, yellow, or orange, or being the key word there. Okay? All right, well, hopefully those rules of probability are pretty simple. So just one more concept we want to cover in today's video, and that's the idea of the multiplication rule for independent events. Now, there's a lot of terminology involved in probability, and a lot of times the struggle for students in this chapter is just keeping them all separate. So we just talked about disjoint and mutually exclusive events, and now we're going to talk about independent events, and know that this is a completely separate term, okay? So we say that 2 events are independent if one event does not affect the probability of another event, right? Then we consider them independent, right? So you think about flipping a coin, right? If I flip a coin and I roll a die, right? We go back to the event that we talked about earlier. Those 2 events are independent of each other, right? What I come up with on the coin is not affected by what I obtained on the dice. Now, a common argument I'll get from students that just want to kind of take the other side of things is they'll say, well, if the coin bounces off the die has affected the coin. Now, that's not what we're talking about in independence, right? And the key to independence is right here in the definition, right? That it does not change the probability, right? So yes, the coin might bounce off of the die, but the probability of the coin coming up heads is still 50%, all right? Those events are independent. And if events are independent, we can just simply multiply their individual probabilities to find the and part. Now, if we look at a Venn diagram here, right? So notice, independent events and mutually exclusive events, very different things. Think back to our mutually exclusive diagram, 2 separate areas, right? In independent events, we're looking at that overlap where they do occur simultaneously. We could say we're looking for the intersect area, all right? So we've got an example problem that we want to look through to do this here, okay? So here's our example problem. Last slide to wrap up our video today. So an athlete is suspected of having used steroids, is given 2 tests that operate independently of each other. That's an important term that we want to recognize. Test A has probability of 0.9 of being positive if steroids have been used. Test B has probability being of 0.8 of being positive if steroids have been used. So the question we have is, what is the probability that neither test is positive if steroids have been used? Okay? So the first thing that we want to recognize here, again, is that word with independent was used. So that means if we want to find the intersect area, all right, we can multiply. And that's what we're looking here for. We're looking for the probability that both tests in reality has failed. Right, so another way that we could read this, instead of saying the probability that neither test is positive, we could say, what is the probability that test A fails and test B fails? And then we get that word and in there. Right, we're representing the intersect. Okay? Well, we're given the information we need in this problem. What's the probability that test A fails? Well, we're not given that all right? But we are given the probability that it's successful, and it's successful 90% of the time. So based on the probability rule of the complement, we know the probability that it fails then is 0.1. Right, same thing with test B. We know the probability that test B is successful is 0.8. So the probability that it fails is 0.2. And again, the word that we used earlier was and. We've said that they're independent, so that means we can multiply these probabilities together. All right? So if we use both tests together, there's only a 2% chance that if somebody did use steroids, that they would not test positive on either test. All right? So that's an example problem there using that multiplication rule for independent events. Now, these are some rules that we will get some more practice with on Tuesday in class, but it's going to be important that you have some background knowledge on them. So I hope you took some good notes today. And as always, if you have any questions, I know we haven't done this in a while, but you need to complete the form below and make note of your level of understanding. And then also, well, let me know if there's anything that you like explained in further detail. So I hope you guys have a fantastic weekend, and I will see you Tuesday.